All right, so our last portion of this unit is really a pretty big portion. It's kind of the second half of it, but it's all about solutions and mixtures and the IMFs that kind of occur within those solutions and mixtures, okay? So our solutions, right, whenever we talk about a concentration of a solution, we always use molarity, which this is a capitalized M, right? Molarity is equal to the number of moles of our solute divided by liters of solvent, okay? So moles of solute divided by liters of solvent, okay? So we should be able to use that relationship to do any sort of our concentration calculations. But within our solutions and mixtures, right, we want to be able to draw particle diagrams. Okay, so our particle diagrams for solutions or mixtures, right, they're going to have two different pieces in it, right? So we should be able to show if we have this in our in a mixture, right? We should be able to show the concentration of a second piece, right? 1, 2, 3. So in this case, what I'm showing is there are 1, 2, 3, 4, 5, 6 of the white or unfilled circles, right? And only 3 of my dark circles. So what I'm showing here is that my concentration is half of the unfilled circles, okay? So I can show concentration. I can show also relationships where maybe I have a solid down at the bottom here, right? The solid down at the bottom, all of those particles are really close together, right? And are all down at the bottom, and maybe I have liquids that are left over up on top, right? I could also show relationships like my ions of chlorine, right? I'm going to do Cl minus interacting with my ion or my water molecules, where my H2O, all of my H ends are pointed towards my chlorine, right? The positive end of one molecule is pointed towards the negative end of my ion, okay? So each of these particle diagrams, what I'm trying to do is I'm trying to show the property that I want to show, right? Concentration, solid versus liquid, or intermolecular forces, okay? So within our mixtures, right, mixtures, we have a substance that has two different compounds in it. We can physically separate it. So we can separate it using chromatography and using our intermolecular forces, right? And the differences between those intermolecular forces, okay? So with our chromatography, right? Chromatography, we essentially have a solid phase, right? That solid phase is going to have either paper or silica. It's going to be really super polar. Okay, so if it's a really super polar substance, right, polar compounds are going to stick to that polar the polar paper, okay, or silica. So right down at the bottom, we're going to put a line, and we're going to put each of our compounds down at the bottom there. And then we're going to put this into some sort of liquid, right, and that liquid is going to travel up the paper or up the silica until it reaches a point. And as it does that, it's going to pull along the compounds that we put on there. So whether or not it can pull that compound depends on the intermolecular forces, right? So if it pulls and it can't move it at all, right, that compound is really attracted to the paper. That would mean that it's going to be a really polar substance. If it pulls up and goes all the way up to the top, that means that it's really not attracted to the paper, and it's going to be probably nonpolar and go all the way up to the top. If it goes somewhere in the middle here, right? So somewhere in the middle, this is where we have to kind of interpret what's happening by saying, okay, it kind of pulled it away from the paper, and if I wanted to pull it a little bit further, maybe I need to make my liquid, right, my mobile phase, a little bit more polar so that I can pull it a little bit further. If it pulls all the way down at the bottom here, right, maybe we want to move it further. We need to make our mobile phase more polar. If I have something that pulled maybe a little bit too far and we wanted to move that down a little bit, right, I would need to use a mobile phase that is less polar, right? Because it's going, the less polar, it's not going to be able to pull the compounds as far, okay? So we have the solid phase, and this would be our chromatography paper, or our silica plate. We have a liquid phase or mobile phase that is going to be doing the pulling, right? And then we have our compound that we put on here. And then depending on how far it moves, we're going to get an RF value. RF value is how far did it move divided by how far it could have moved. Okay, so how far it could have moved would be all the way up at the top where the mobile phase stopped. Okay, so with each of these, right, what we kind of need to remember is that intermolecular forces, they're going to stick together when like interacts or goes with like, right? Like goes with like, or like dissolves like. Okay, so if we have similar intermolecular forces, right, then it's going to stay with that substance, okay? We will get more practice with this in the lab, all right? This can also be used similarly, right? We can use our chromatography to separate by intermolecular forces. It's the same idea with distillation. With distillation, right, we start from liquids, a mixture of liquids, and we're going to heat it up until one boils. Okay, so when we hit the boiling point of one substance, right, we're saying that we're giving it enough energy to break the intermolecular forces and go fly as gases, right? So distillation is again separating it by intermolecular forces, right? So when we heat it until we hit the first boiling point, we're going to collect whatever gas that comes off, and then we'll keep on heating it until we collect the second gas that would come off, okay?